We'll get started. Just a couple of reminders if folks were still looking to get some of their assignments in. Your case study peer review is due today at 11. So is quiz 2, as well as your weather data sources assignment. This is the last and final week of coursework. And so this week is going to be focusing on characteristics of extreme fire behavior. With that, we are going to kick it off with Danny Goddard, and I'll let him introduce his topic. And himself.
Okay, good afternoon, everybody. My name is Danny Goddard. I work currently as the fire operations specialist for New Brunswick here on the East Coast. I've been in wildfire for about 25 years, involved as an F-band for about the last 10 years. And today we're going to talk about extreme fire behavior and the part that fuels plays in it. Tanya, I might need some help sharing this screen with the speaker notes. I can share the presentation, but not I didn't want to share the speaker notes.
That I'm not sure about. I've never mastered that either.
Anybody else in the audience? Okay.
Yeah, I think it's just a straight up share.
Okay.
Yeah, that's PowerPoint. Yeah, if you're in full screen mode, you shouldn't have your speaker note showing, I don't think so.
Hey, Danny, you can also just go into PowerPoint and there'll be a present in Teams button at the top right or top left.
Yeah, that's not working, Sam. I thought that would work too, but it didn't work.
Ah, well, I got nothing for you.
Okay. Yeah, sorry, PowerPoint. So I kind of played with this a little bit and figured this would happen. So I brought 2 computers today so I can look at the speaker notes. Would have been a little bit easier.
Yeah, I mean, if you've got 2 monitors, there's that, I can't remember what it's called precisely, but kind of I switched to presenter view or something like that. You have to go into full screen mode. But,
how does that work? Can everybody see that?
It's looking good.
Yep.
Okay, I'll just run the 2 screens. So I can't really see what's.
Danny, if you like, I can moderate. So if somebody throws up a hand or there's something pertinent in the chat, maybe I'll give you a signal.
Okay. All right. So Unit 3 talks about fuels, surface weather, and topographical influences and their effect on extreme fire behavior. And this part A, we're going to talk about the fuels part. So the learning objectives for this are we're going to identify the complex interactions between various components of the wildland fire environment leading to extreme fire behavior situations. We're also going to describe the changing fuel environment, fuel treatments, climate changing, fuel buildup due to fire suppression, and the potential impact on fire behavior. Whoops. Okay, so fuels are probably the most important component in the fire environment triangle, yet they're in many ways are the least understood. They play an important role in understanding how a fire is going to move and when, and careful consideration needs to be taken when assessing these fuels before we lump them into a silo of a fuel type. We need to observe, examine, and experiment with on-site fuel types to understand when and how they will react. So it's already been talked about a few times that usually when you get to an incident, the first day or so. If you don't have your fuels really assessed, you can be pretty off on some of your predictions. And this has happened to me a few times. So we can fall into the habit of just putting characteristics of fuel into these broad categories of crown fuels, ladder fuels, surface fuels, ground fuels, and the mineral soil. In nature, we as humans have become trapped and look through a lazy, simplified lens and categorize fuels with the same brush. Yet fuels can span a full spectrum of live and well to dead and decomposing. And fuels have a multiple states and conditions when they're influenced by weather and topography. And we've talked about this quote before, but if you fought forest fires in every different fuel type under all possible different kinds of weather, and if you remembered exactly what happened in each of these combinations of conditions, your experienced judgment is probably very good. But if you've not fought fire in all sizes of fire in all kinds of fuel types under all kinds of weather, then your experience does not include knowledge of all the conditions. And that's a quote from Gisborne in 1948. And, it's different. It's been different at every incident that I've ever gone to, and I'm sure that you will as well. So this is something new here. This is the what we're getting away from the triangles onto other geometric shapes. And this is called the fuels pentagon. In it, we can see it contains chemistry, quantity, density, geometry, and continuity. And all these characteristics are very important to fuels in smaller scales and also across the landscape. So the chemistry of the fuels. Fuel particles are composed of 5 broad chemical categories: water, carbohydrates, fats, proteins, and ash, or ash is also considered the mineral content. In dead, sound, woody material, water can compose only a small fraction of the total mass of the fuel. While in dead, rotten, woody fuels and live fuels, water can make up to 50% of the fuel's total mass. The remainder of the fuel's total mass is distributed disproportionately across the remaining 4 fuel environment categories. A fuel fraction allocation to different categories of chemical compounds varies substantially depending on whether the fuel is alive or dead, and for different parts of the fuel, such as the leaves and the branches and the stem. So fuel moisture content has long been considered a factor in driving fire behavior. When fuels are heated, some of the moisture is evaporated and pyrolysis is taking place, or a breakdown of the fuel. Therefore, moisture content must account for at least a portion of the ignitable fuels. The heat of water is 4 times that of any chemical component found in wildland fuels. A lot of energy has to go into raising the water to a boiling temperature that could otherwise be used to raise the fuel to ignition temperature and create the gases for support flames. Logic suggests that all moisture must be removed from a fuel particle before significant pyrolysis can take place. However, research suggests not all water in a fuel particle must be removed prior to ignition. Moisture content must account for at least a portion of the ignitable fuel's mass. And carbohydrates. Carbohydrates make up a large percentage of the wildland fuels. They can generally be classified as either structural or non-structural. Structural carbohydrates give strength, form, and stability, and non-structural carbohydrates serve as energy reserves for living plants. These carbon-based compounds provide the primary substrates for the gases that contribute to flaming combustion. And fats and proteins. Fat-based compounds make up 10% or more of a fuel's dry mass. These compounds are generally composed of waxes, oils, resins, and isoprenes. Fats are an important fuel component because they can potentially release twice as much heat as other leaf compounds. Small changes in fat can cause large changes in the fuel's flammability. And the minerals or ash content is a measure of the amount of the fuel that's composed of unburnable compounds. Ash is quantified as the content or ash fraction of a fuel measured as the remaining biomass after complete combustion of the fuel sample. The geometry. Surface area to volume ratio is a fuel property that describes individual fuel particle geometry and strongly influences flammability, fuel temperature, and moisture dynamics. Surface area to volume ratio is often assessed based on the measurements of diameter. However, assignment of fuel size classes based on diameter is only valid for fuels that have a cylindrical or rectangular geometric shape. Surface area to volume ratio also forms the basis for the concept of time lag classes. And here they are here. The concept of time lag classes is based on the amount of time required for dead fuel to lose approximately 63% of the difference in between its initial moisture content and the equilibrium moisture content in the atmosphere at that time. 4 time lag classes are currently used. In dead fuels, they are 0 to 2, 2 to 20, 20 to 200, and greater than 200. We use class midpoints when we describe them: 1, 10-hour, 100-hour, and 1,000-hour fuels. And I'm sure a lot of you have heard those terms before. Time lag size classes have been widely used to assist in describing the fuel mass and distribution of fuel sizes within an area. In general, fine fuels tend to combust more rapidly and have been associated with several firefighter fatalities and close calls. In addition to the information regarding particle size, the distribution of fuel particles estimates of the fuel masses within an area. The arrangement of fuel are other important variables that influence fire behavior. Fuel arrangement pertains to the packing ratio or compactness of fuel particles, as well as the vertical and horizontal continuity of the fuels. In most empirical and semi-empirical fire models, fuels are assumed to be homogeneous and continuously arranged. However, in real-world situations, this seldom occurs. The effects of heterogeneous arrangements and deviations from continuity on fire behavior are not really well understood. The quantity of fuel available for combustion is a key factor in how fires burn. Fuel quantities are often expressed as loading in terms of mass per unit area, such as tons per acre. Determination of quantity of fuels by class is one of the fundamental assessments in conducting a fuels inventory. And then we can see it's tons per acre or the metric alternative. Quantity, there are several definitions commonly used in the assessment and communication of quantity. The 3 most common are total fuel mass, potential fuel mass, and available fuel mass. So the total fuel mass or total biomass is often considered the amount of combustible material present in an area. And the potential fuel mass is the amount of the entire fuel mass that could burn in the hottest part of the fire. The available fuel mass is the amount of the total fuel mass that will be consumed for a particular situation. In some cases, these three values may be very similar. However, in most forested fuel complexes, the values will differ greatly. Fuel masses by size classes or one of the above-mentioned groups are often required as inputs in mathematical fire models. Density. Density is the compactness of fuel particles in a fuel bed and influences several processes related to combustion, including heat transfer, oxygen diffusion of the fuel bed. The simplest measure of fuel compactness, commonly used to describe the canopy fuels, is bulk density. Bulk density is a measure of the weight of fuel per unit volume and includes not just the fuel particles, but also the space between the particles. The concept of bulk density can be applied to either surface or crown fuels. In mathematical fire behavior models, the bulk density is often converted to a packing ratio. Rothermel defined the packing ratio as the fuel bulk density divided by the particle or material density, such as the volume of a solid block of wood. Thus, the packing ratio is really a dimensionless number used for reference. The concept of bulk density can be applied to either surface or crown fuels. In mathematical fire behavior models, canopy bulk density has been incorporated as a primary variable influencing crown fire spread in several fire behavior prediction systems, and it's included in a fuel hazard assessment. And we'll talk about that a little bit more. Continuity refers to the degree to which fuels are uninterrupted. At larger scales, horizontal and vertical fuel continuity is very important for fire spread. Another fuel characteristic with important implications for extreme fire behavior is this horizontal and vertical continuity. It can be considered at the scale of a single particle, but it's quite important to know how fire burns across a collection of particles. At the scale of individual particles, such as surface beds or leaves or needles, fuels are often considered to be continuous, even though there are gaps between particles because of the size of these gaps. They're small and they're compared to the typical flame sizes as fires burn through that fuel bed. Okay, so we really need to think about continuity when we think about surface to crown fire transitions, and continuity is captured through an estimation of the canopy base height. Canopy base height is defined as the lowest height above the ground at which there is sufficient canopy fuel for the fire to propagate vertically. And this is, however, difficult to directly measure. Several methods have been used to estimate canopy base height, including the height at which a given amount of canopy bulk density exists, the mean crown base height, the lowest crown base height, and the percentile crown base height. So vertical continuity influences vertical fire movement among fuel layers, such as surface to fire transition. In mathematical fire behavior models, such as Rothermals and Van Wagner, fuel is assumed to be homogeneous and there are no spatial variations considered. Horizontal continuity is primarily related to the spread of fire across a landscape. One important aspect of continuity is the spatial scale at which we consider this variable. So looking at the fuel pentagon again, operational fire behavior models in Canada currently do not account for spatial variations in vertical and horizontal continuity. Despite difficulties in quantification of spatial continuity and a lack of modeling methodologies able to account for spatial continuity, a lack of horizontal continuity can reduce fire rate of spread or completely prevent spread in extreme cases, and we see this in fire suppression. Conversely, increased horizontal and vertical continuity can increase the potential for fire spread and crown fire initiation. The disruption or alteration of vertical and canopy fuel continuity has been used to guide fuel management operations and fire suppression operations. The removal of fuels through the construction of fire line operations reduces horizontal fuel continuity and with the goal of preventing further horizontal spread. And I'm sure you've all seen this when we create guards around fires. In this next section, we're going to discuss how broader patterns of fuels can lead to such combinations at a landscape scale. So we're looking at the individual fuel particles before, and now we're going to start to look at how those things affect fuel on the landscape. So the role of fuels in extreme fire behavior is complex because of all the fuel characteristics in the fuel's pentagon. Once they start to interact with one another within the fire environment. So far, our discussion of fuels has focused on the fuel characteristics that influence flammability at fine scales, particles, and small collection of particles. Changes in fundamental fuel characteristics over time arising from one or more factors can lead to changes in likelihood of ignition, rate of spread, or intensity. Fuels are highly susceptible to changes arising from interactions within the environment, often in complex ways and across multiple spatial and temporal scales. So fuel patterns on the landscape are complex because they result from interactions between the processes of growth and succession. These typically cause fuel accumulations and natural disturbances processes such as fire, wind throw, insects, and pathogens which kill individual plants and alter vegetation composition and structure. Disturbance processes or natural disturbance processes are integral parts of the natural system and play a key role in regulating fuel masses and other characteristics, as well as opening up space for new plants to grow. We'll begin with a discussion on landscape fuel distribution patterns and fuel changes that are driven by natural ecological processes. We then discuss how fuels distributions and characteristics can be affected by management actions, such as fire suppression. So natural fuel changes. Natural systems are in a constant state of change as plants respond to the environment, grow, and compete for space and other resources. Many fuel changes are directly related to weather. Live understory grasses, which may be unlikely to burn, can greatly increase flammability if there is a killing frost. Diurnal shifts in fine fuels on a hot day can rapidly change ignition potentials and surface fire rates of spread. Fires have been observed to significantly increase in intensity over a few seconds simply because the sun comes out from behind a cloud. Desert ecosystems in which fire has historically been limited by low fuel continuity can burn extensively after cheatgrass invasion. High elevation forests, often too wet to burn at one time, can burn now greatly with great intensity after a drought. Fuels interact with weather and climate in several important ways spanning different temporal scales, changing from diurnal to seasonal to interannual. These interactions can significantly increase extreme fire behavior. So just to touch on these a little bit, the temporal dynamics, like over time, fuels change a lot, and they can change within hours. We see it in the diurnal trends of temperature, relative humidity, and wind fluctuation, affecting fuel moisture content by the hours in the day. These diurnal fuel fluctuations can strongly influence fire behavior. Generally, the lowest diurnal moisture contents for both live and dead fuels are observed during the hottest and driest parts of the day. Seasonal fuel changes throughout the year because of cumulative effects of weather and their biophysical cycles. Early in the spring, prior to green up, last year's grass may be dry enough to burn, and fires might ignite and spread. Shortly after green up, though, the live surface fuels with extremely high moisture contents may impede fire spread until later in the summer, when these fuels are cured and dried. On the other hand, freshly fallen leaves from a deciduous forest often contain large air spaces between individual fuel particles. However, as these leaves become compressed and decay, their surface fire potential decreases. Interannual climate scientists have identified a number of different climate patterns, such as Pacific Decadal Oscillation and El Nino and the Arctic Oscillation. I'm not going to go into them too much. That would be a very good question for Richard. But these patterns often span over 2 or more years, and some of their droughts can debilitate some species. Things like drying out the foliage and increasing flammability over extensive areas. The cumulative effects of that is a reduction in leaf production can also reduce the litter quantities. Depending on the ecosystem, climatic changes, and site productivity, surface fuel loads can increase rapidly if deposition exceeds decomposition. So these patterns can emerge over years of these weather patterns. Successional is over a longer time scale. Fuels will change along with vegetation through succession. The process by which ecological communities change in species composition and structure over time changes as new species grow and older species die. So how do fuels react to change on the landscape? Well, weather, curing, frost, diurnal changes, time frames, they can be daily, seasonal, or they can be a lifespan. In this graph, it displays the seasonal trend in coniferous foliar moisture content and the resultant crown spread fire factor for the Petawawa Forest Experimental Station in Ontario. So I don't think that graph is going to surprise anyone, but as you can see with the lower foliar moisture content, it's more likely to have fire spread into the crowns of the trees. So these natural disturbances, they can promote rapid changes in fuel composition and structure. Many disturbances such as fire and pathogen attacks are regular occurrences and may generally be limited in extent. Other disturbances such as climatic changes, wind throw, management action related impacts, and non-native invasive species may also significantly affect the fuel complex. These types of disturbances alter some or all of the components of the fuel's pentagon, and thus significantly affect expected fire behavior. Wildland fire disturbances. Their disturbance processes influence the accumulation of fuel and the nature of the fuel characteristics on the landscape. In most regions of the world where fires dominated disturbance, vegetation shows evidence of adaptation to fire with characteristics that tend to promote fire under conditions favorable to that adaptive strategies of those species. Pathogens and insects. Forest pathogens and insects are affecting large areas of North America. Many of these pathogens and insects are natural parts of the disturbance cycle of forests, and endemic attacks are common and help to maintain uneven age stand structures. The interaction of pathogens and insects with their host, as well as their ability for spread, influence the rate at which mortality occurs and therefore influence the resulting fuels complex. Often our understanding of how fire behavior changes in insects and pathogens infested stands is still limited, but it's an area of active research. Anyone that was at the Wildfire Canada conference, there was almost a morning session devoted to how pathogens and insects are affecting extreme fire behavior. Wind disturbances such as hurricanes, tornadoes, blowdowns, and microbursts can greatly affect the fuel structure of given ecosystems. And they can alter those fuels in minutes. In general, leaves may be stripped from standing trees, branches and whole stems may be broken and deposited as surface fuels, which significantly increase surface fuel masses. Following wind events, surface fuel masses are found to be almost twice as high as those found in adjacent undistributed stands. And just we're seeing this now on the East Coast with the hurricane damage that has happened over the past couple of years. We're getting a huge load of hurricane fuels in places like Prince Edward Island and Nova Scotia, to a lesser extent New Brunswick, but it completely changes the fuel complex. And if there is a fire, you know, it's going to be devastating. Anthropogenic changes in fuels, or anthropogenic is human-caused changes. Some fuel changes have been induced by human action or inaction. Human activities can affect extreme fire behavior by changing the dynamic interactions between succession and natural disturbance processes. Anthropogenic influences can also distribute fuel continuity, reducing the likelihood of fire spread. Fire suppression plays a role in altering fuel masses and continuity. Fire suppression is often considered to have resulted in increases in fire intensity and resistance to control efforts. This appears to be the case in North America, as many dry forest types where fuel accumulations related at least in part to fire suppression have resulted in intense fires uncharacteristic of those frequent fire regime areas. Fire suppression limits the reduction in surface fuels that are common in areas with short fire return intervals and allows for the growth of shade-tolerant species in an understory that often serve as ladder fuels to carry fires from the surface into the crowns of the trees that might not normally be affected by low-intensity surface fires. Just an example of this, there was a fire a few years ago in 2019 in High Level on the Chuckegg, and I was an FBAN there, and I was really startled when the forest manager or person in charge of the forest area there came into the trailer one day, and he was quite upset, and his exact statement was, "I want everything set on fire around this city." And it really, coming from kind of a mindset of put the fire out, his explanation made total sense. This was, we've been putting fire out for 120 years in the boreal around this town. And he said the fuel load around it is greater than it's ever been. And he was totally right. So, just to change different mindset and to hear that type of mindset, really made you think about what the fuel load is in and around areas that we have been putting fires out. And I'm sure you guys have had lots of experience with that. And it's a big problem on the East Coast as well with the heavy fuel load. Fire managers face the prospect of ecosystems that are changing rapidly and often in several ways at once. Many of these changes are exacerbated by climatic changes. Climatic changes can influence extreme fire behavior by altering both the short-term fire weather and influencing longer-term changes in vegetation, composition, condition, and structure. Understanding the implications of these changes is essential for determining and potentially mitigating the role of fuels in extreme fire behavior. Changes in climate have significant implications for fire management in the future. Climate shift towards hotter and drier conditions can greatly alter the likelihood of events. Hot and dry events that may have been rare historically, as we can see under curve A, may become much more common, as we can see under curve B. And maybe 2023 fire season was an indication of curve B, where we are seeing these weather events being locked in an area for a long time, causing problems with fuel, drying fuel out too much. Climate change. Although climate change is represented as controversial in the popular media, there's little debate in the scientific community that climate change is occurring and that it is anthropogenic in nature. Globally, climate change is resulting in increased temperatures, widespread melting of both polar and continental ice, and causing a sea level rise. Changes in precipitation vary among the regions. Earlier spring snowmelt dates combined with higher temperatures have lengthened the fire season, and this trend is expected to continue. The shift towards increased temperatures may significantly alter the likelihood of occurrence and weather patterns associated with extreme fire behavior. At regional scales, climate change effects are expected to spur increased fire activity. And there's probably not too many people in the room that are going to argue with that statement. So, shifting landscape and species distribution. During this change, existing species at the tree line might experience competition from lower elevation species expanding into their range. In some cases, temperature changes may differentially affect fuels at different elevations. For example, During an extreme heat wave, vegetation at low elevations was severely water stressed, while vegetation at higher elevations grew more vigorously because of a snow-free period that was lengthened. Shifts in species distributions are typically expected to take place slowly. However, recent evidence suggests that they can occur very rapidly when thresholds of environmental conditions are passed. Currently, there's a widespread tree mortality has been observed in the temperate forests of the western United States. In the short to medium term, these die-off situations can represent a potentially disastrous increase of flammability, leading to an increased risk of extreme fire behavior. Over longer time periods, if persistent, these climatic effects may result in a whole different species composition and structure, such as a shift from forest to lower density woodlands or from shrublands to desert. And invasive species. So I haven't seen this too much, but fire managers must adapt to the spread of invasive species. Invasive species can either be native or exotic. Exotic species generally refers to any species that falls out of its native range. They're usually from other continents, but many native species can also be considered invasive if they move into areas that they did not otherwise occupy. Both native and exotic species are significantly alter fuel dynamics. Where invasive species are physically similar to other species, such as the invasion of grass into an ecosystem already dominated by grass, they tend to alter fire behavior by changing fuel masses. In contrast, when the invasive species have no history within a given ecosystem, they can significantly influence the disturbance cycle of the system into which they're introduced. While these species also alter fuel masses, they can also change fuel characteristics such as continuity, density, and chemistry. And this can essentially affect how fire spreads. Epidemic insect and pathogen outbreaks. While frequent low-intensity pathogen and insect attacks are common, occasional pathogens or insects may rapidly reproduce and attack vast areas, killing vegetation and altering the fuel structure. These attacks can induce widespread rapid changes in the fuel complex that can last for decades. One example of an epidemic outbreak is the current widespread infestation of mountain pine beetles. These outbreaks generally occur when there is an abundance of host vegetation, high concentration of pathogens, and favorable weather. Fuel changes following an outbreak are very dynamic, and these changes can either increase or decrease expected fire behavior by changing all 5 sides of the fuel pentagon. For example, foliar moisture content drops rapidly after a successful attack, altering the fuel's chemistry and little else. Later, when dead aerial vegetation falls to the ground, surface fuel masses, continuity, and geometry are altered. All these changes manifest themselves as changes in the potential for extreme fire behavior that can span millions of hectares in some instances. And I think every part of Canada probably has seen some of this, insect attack. Fuel management options that reduce extreme fire behavior potential. Reduce surface fuel, increase crown base height, decrease crown bulk density, and retain large fire resilient trees. So I don't think anyone that's involved in FireSmart or anything, I don't think this is anything new. Fuels, weather, and topography interact and dictate how fires burn. However, fuels can be manipulated to lessen extreme fire behavior potential throughout different fuel management strategies. The terms fuel management and fuel treatment are often used to denote activities that are undertaken to either meet some land management or ecological objective or to reduce the potential for extreme fire behavior. Various fuel treatment actions are undertaken to change one or more of the elements of the fuel's pentagon, thus in turn having an impact on potential fire behavior. Fuel treatment projects are objective driven, where a particular problem is identified and many options are evaluated to meet that objective. Ultimately, some strategy must be developed that alters fuel characteristics and achieves specific and ideally measurable reductions in the potential for extreme fire behavior. And then primarily there are 4 types of fuel treatment actions that can be undertaken to achieve these. Reduction and redistribution of surface fuels, increasing height to live crown, decreasing crown density, and the retaining of large trees of fire-resistant species, as we already talked. Negative influences on fuels treatments. Fuels and weather are strongly coupled and interact to influence the microclimate of a given stand. These couplings and interactions are important to consider when developing strategies for fuel management. Activities such as thinning, while effective at reducing crown bulk density, they may also increase surface wind speeds because of the reduction in aerodynamic drag. Additionally, removing trees may increase the amount of solar radiation that reaches the forest floor, potentially influencing surface fuel moistures. Ultimately, strategies aimed at effectively reducing the likelihood of extreme fire behavior must be considered within the context of both the direct changes in fuel characteristics and the indirect influences on other components of the fire environment. So to summarize this unit, I think I'm a little early, but pretty close. The complex interactions between various components of the wildland fire environment, i.e. fuels, weather, and topography, leading to extreme fire behavior situations. Evaluate the effect of changing the fuel environment, human influence treatment, climate changing, fuel buildup due to fire suppression, and the potential impact on fire behavior. So throughout this talk, we generally attempted to paint in broad strokes the role of fuels in extreme fire behavior. We demonstrate that fuels play a critical but complex role in which key characteristics of fuels summarized in the fuels pentagon and their composition, arrangement, and landscape pattern that can change often rapidly in response to both human and natural influences. These changes can result in significant increases in flammability and how fires will burn across the landscape. We bring in the big picture view of the dynamic landscape, changing in many ways at the same time and across different scales in response to climate change, anthropogenic activities, and feedbacks with other agents of change such as invasive species or beetle epidemics. All these factors play a role in the occurrence of extreme fire behavior. With hotter, drier, longer fire seasons, prolonged drought, invasive species, and large-scale beetle attacks all affecting wildland fuels looking ahead, it's apparent that extreme fire behavior is not going to disappear. Faced with these challenges, our best answer is to build stronger ties between the fire science and the fire management communities and work together. That is the presentation on fuels and how they affect extreme fire behavior. Anybody got any questions?
Well, that's a lot of information to digest. We are early. I think this presentation was set to run until 12 o'clock Mountain. But maybe let's take a 10-minute break and come back, because I know that I'm sort of curious whether or not folks have what sort of fuels issues have you guys encountered on the fires that you've been on? I know that there's a few folks in there from BC and a few folks from out east, because there's some unusual fuel types out there. So why don't we come back at the top of the hour and we'll have a bit of a chat. You good with that, Danny?
Yeah, that sounds good. Yep.
Okay. See you soon.
Does that mean you can call? I just gotta turn my camera off. Oh yeah, I can.